as mentioned before, I wanted to show in the hands-on how we can use this entire language agnostic framework to perform graph neural architecture search for molecular property prediction. Since I've already done a recap on graph neural architecture search and the way we train graph neural networks, I'll go more into the process of building this. And before I go in, I wanted to showcase two examples which would give a decent idea as to how MetalGPY, the power of the expressiveness of MetalGPY in its ability to transform any Python program into a symbolic expression. So that would mean your TensorFlow model, that would mean your scikit-learn model, that would mean as simple as an algorithm of a traveling salesman problem. So the idea is to use the decorator to transform your given code into a symbol, and then use a set symbol to build a program that could be used to perform any sort of optimization task. The optimization is not a compulsion, but it shows you the capability that it's possible. So in this program, the function is a simple program. It again returns just the square of a given number, and you've created a program out of the set function, creating a lower bound and upper bound, and the program just shows you the possible choices of the symbolized program, and then using mpy.sample, you can optimize the program. So this was a pretty straightforward example I showed you on the slides, but I would show you another example where I'll actually of doing arithmetic expressions. So say you have a small operation, say you have a binary operation, right? And say you try to create a class, and you try to transform your given class into a symbol in such a way that you build an arithmetic expression based out of symbols. So that would mean you could do something like this. So that would mean you can do something like this, which is my operation space in mpy.sample of meta p size equals to just say 4. Then you can say, okay, operation choice would be meta op.clone, as I mentioned before, and freeze of a specific operational choice would instantiate a specific value to the operational choice, and operation just be operation choice dot evaluate. Now you can see how you can use the operation to perform something as simple as this. So for a given two numbers, 2 and 3, it shows you how it tried to perform different arithmetic operations, and each of these operations are evaluated only when you hit evaluate, and you can see how expressively it tried to convert a very simple arithmetic operation into a symbolic expression, thereby making this much more expressive than your normal Python programs, I guess. So let me go into the GraphNAS part and the molecular property prediction part. So for the task of doing molecular property prediction and GraphNAS, we try to employ the molecule net dataset. It has the different components. For this specific hands-on, I'm just going to use one dataset. I'm not actually going to run it. I'm going to show you how it's possible to tease out the search space, just like how I showed you with any other program, it's the same with building a graph model. So for the training purposes, we try to mini batch the graph into smaller subgraphs, just because this is much more computationally beneficial, and it just diagonally puts it diagonally stacks all of the adjacency matrices into one large graph. So say we have loaded the graphs, say we have we have created the data loader. I wanted to showcase how in one of the slides I showed you how you have an architectural component space and then have an algorithm component space. Now, if I try to run this for a specific choice of encoding the model, for a specific choice of message passing, for a fixed number of hidden layers, for repeating the same convolutional block a number of times, and a specific choice of skip connections, you essentially have a model. So think of this, the number of millions of possibilities, the number of millions of models that you can construct from this specific form. So ideally, like Prasanna mentioned before, you're creating a template which could be used to create which would be the basis for you to create all of the set programs. So instead of manually encoding this, the expressiveness of MentalGPY transforms your given program into symbolic programs. So I just wrapped the message passing model that class that I built with the decorator, and I encoded in all of the variable choices that are possible, and bam, voila, it just shows you all of the different combinations. So the same loop that you're seeing in this specific cell is similar to all of the previous examples that I showed. Ideally, the point being that it shouldn't be any similar to run this as and when compared to a simple square program. So so you have your PyG model space, and it shows you the vectors for each specific sample that it picks. And once you evaluate the model, you can see it evaluated the said PyTorch model, and it shows you the model that which has been called. So you can do the same thing. And once you incorporate a report, like I mentioned before, it creates a Bayesian optimization loop. And that is what you can see over here. You can play around with these upper parameters, and you can play around to increase the space of the search, the complexity of the search. But that's pretty much it. You can transform a simple message passing model that you built and do neural architecture search, graph neural architecture search for molecular probability prediction. So,
excuse me, could I ask a question?
Yeah, sure.
Is there so typically when you wrap things in abstraction, there's always some performance penalty. So where
could you repeat that again?
Is there a performance penalty in wrapping ordinary functions symbolically like this?
I mean, since essentially all of this has been boiled down to an expression tree, there isn't a performance penalty, because I tried to run different general purpose programs and different machine learning models to see if the values that are returned, the time it takes to run a normal program and a symbolized program would be any different. I didn't notice any difference, but I think a larger scale study would give us a better indicator, much more like an objective metric to see if there really is any performance measure, because we didn't see any from the unit test that we ran, at least.
Mm-hmm. What about during backpropagation? I imagine if you wrap a model like this, does it create like effectively more layers for gradients, or is it somehow removed from that?
So Ian, I can take this question. So this is independent of the back propagation. So think of this back propagation happens after you create the program from the template, right? So that you have the template, you have the search space, the Bayesian optimization selects parameter configuration, send it to the template, and then from the template you generate a program. That program is, let's say, a TensorFlow code or a PyTorch code, okay? And from that code, what you do is do model training, okay? And you get the validation loss, and you send only the validation loss back to the Bayesian optimizer. So the backprop or the number of layers, these are all independent of what is happening at a higher level in the meta-alpha. Does that answer your question?
Yeah, that answers the question. Thanks.
Okay. Go ahead, Akhil. Is there any other questions?
Yeah, I think that was the last cell.
Okay, great.
I would encourage people to play around with this notebook and see if you can incorporate MetalGPY into your current workflows. I would definitely urge everyone to go to the repository, show us some love, hit a star, and try to share this, or if possible, it would be of great help if you could use it in your workspace and let us know if you faced any issues or any good performance. But that's pretty much it.
Akhil, related to the question of Jan, can you maybe show again the example of scikit-learn, to show what is the base code and what will it be in a...
Oh, yes.
Yeah, sure. You can. It's in the example folder.
Yes. 1 second. So if you can see, the original code was created using the scikit-learn's classifier with a specific number of neighbors. It gave the output of a specific metric. And once you have symbolized the said classifier and giving a variable choice for the number of neighbors, if you use the same value that you've used before, it will still give you the same metric. And I'm sure if we have a time metric to see how much time it runs for that and for this, it would be similar, because we're not actually trying to evaluate something until we decide to evaluate it. So quite naturally, when the function call is happening, it's pretty much similar to a variable choice that you've picked. So
Jan, does it answer the question? Is it clear like this?
Probably, Ian, you are muted.
Sorry. I guess my question was, when you wrap these type of models in the symbolizer, is there a performance overhead? That was basically what I was trying to understand.
So let me go through the example line by line here. Line 27, for example. We wrap the can neighbors classifier to become a symbol with the meta, okay? So at this time, what is returned, the CLF variable, it's a symbol, okay? Now, next line, 28, we do fit, a get, it's a symbol that represents the expression call of fit on CLF, okay? Next line, CLF.score, again, score is a symbol, okay? Now we continue. We do score freeze and neighbors 3. Now we fix the value of the variables for the symbol score and neighbors to 3. Now that we have this fix, we can do score evaluate. Once score is running this evaluation, you run the chain of expression. So here, yes, you will have an overhead to, if you want, go back in the tree of the expression and interpret it like Python will interpret code, but here we interpret the expression. However, in the example of Akhil in the notebook, if you wrap just at the object level or at the function level, when you execute the evaluation, it directly executes your function or it directly returns your object. So if you return a model, for example, and then you have the instance of this model in a PyTorch instance or in a TensorFlow instance. Then you train, you don't have overhead. Is it clear?
I mean, the question is how much overhead. I think there is overhead because we have to keep track of the expressions, right? So, but what we've observed so far in the PyTorch example on the graph neural networks and so on and so forth, it's not significant. But there, so compared to the code where we write the code versus, where we go from the template to the code, there is a little bit of overhead because of the expression tree. So I think the question is related to that. And if so, is it expensive or not? Often these are not expensive compared to the training time of that particular script, right? So, probably we are talking about microseconds or even less than that.
Okay, yeah. So if I understand you correctly, so I think that the nomenclature is in TensorFlow, they call it a tape, maybe. The term for when you chain a bunch of operations together and you evaluate it. So I'm going to call that a tape. So what you're saying is because you're just swapping out parts of the tape for each other, but you're not changing how those operate on like an accelerator or anything like that. You're not changing the weights or anything in them. And so there's no performance penalty for forward evaluations or anything like that, backward gradients. But if you were doing, and I don't know why you would do this, but if you were doing like normal mathematical operations in vanilla Python, just using the interpreter, then you would see pretty significant performance penalties, but that's not how we use it. So that's why it's okay.
Correct.
Yeah. Okay, I think I understand. Yeah. Thank you for taking the time to explain that. It seems like a very promising way to, rapidly try different model without having to parameterize everything.
Yeah, and also take an existing code and just add this sort of decorators inside the existing code and expose the parameters, right? So, and then we can plug it inside a Bayesian optimizer and we can do search over different instantiations of the program. This is the route that we are also taking to make the framework agnostic to TensorFlow, PyTorch, or different type of frameworks. So this was a question that was asked. So the current hyperparameter search that we have in the DeepHyper is agnostic to the underlying framework, right? So TensorFlow, PyTorch, not a problem. Julia, or any black box function. The architecture search is sort of depends. The architecture search uses Keras TensorFlow, so it is sort of doesn't handle the PyTorch, for example, PyTorch layers. So the meta-alpy, on the other hand, what the demonstration is on PyTorch, and in fact, it's PyTorch geometric. So with this, we can do architecture search on PyTorch or TensorFlow or whatever, JAX or Flax and Julia even, for example, right? So those are the sort of advantages of making this more sort of a meta template program as opposed to operating at a level of the framework.
I would like to just add one more point to what Prasanna said, because he beautifully summarized all of it. It is, I think the takeaway would be to reimagine how we construct Python programs. So we want to think of it as we're trying to construct symbols that could be mutable in the truest sense of the word, because these symbols that you have created by transforming your given Python code could be used for optimization, could be used for sampling, could be used for anything. So it's trying to think about these programs in a different way, that these are mutable programs but not immutable. So
great.
Yeah.
Other questions, either related to this topic or other topics? Okay, I think we are. Yeah, go ahead, Sandeep.
So there are these frameworks called Onyx, right? So they are kind of used as a common language to convert between PyTorch and TensorFlow. So I was curious if if that is similar to the metal GPY.
So Onyx is after you train the model.
Yeah.
After you train the model, so it's basically just how you save the model somehow.
Yeah, once you save the model, you can it's a cross format and you can port it in across different platforms and things like that. I mean, different frameworks. So Onyx assumes that you already have the model, right?
Awesome.
So this is about generating that model.
Great, thank you.
Yeah. Okay, other questions? I know it's a very long day. Thanks for hanging with us. It's densely packed, and we covered a lot of topics. We perfectly understand that you will be tired by the end of the day, and it's also a Friday, so I don't want to keep you longer. But again, thanks, Akhil, and thanks to all the presenters. Wouldn't be possible without you guys. Coming up with a fantastic set of talks and notebooks, and also thanks to the support team here at Argonne, and more importantly to the participants. Very lively discussions, and honestly, I didn't expect, but it was fantastic. It was also very, very useful for us to get your feedback. It was fun to interact with you all, and we look forward to see how you use some of these capabilities. We are happy to support if you have questions, and sort of follow up on this workshop. We'll send a survey. Please do respond to the surveys. That will help us to sort of identify what our strengths and what our weaknesses are, and that will also help us to sort of improve not only the workshop content but also the software itself. So please take a look at the documentation. Please take a look at the repo code and say, comment, make changes. And more importantly, if you are willing to contribute, please do. DeepHyper is a community effort, and there are a lot of interesting things happening, as you have seen, and we couldn't wait to add more people into the team. And I think we already mentioned this is an open source with permissible license. So please come in, contribute, use it, break it, and let us know you broke it, and we can take it from there. So with that, I'm almost like to conclude, and thanks again. Thanks everyone. If there are no more pressing questions or topics, let's go and wind up. And it's the end of the week. So happy Friday and happy weekend.
Prasna,
yes,
I just wanted to add one thing.
Yes, please.
If anyone in the audience, use DeepHyper and does some research using DeepHyper, and you publish a paper related to this, we will be happy to advert this paper on our webpage and mention that you contributed to the evolution of the software. So do not hesitate to let us know about your use case, how you use this, and if it works. Thank you very much.
Yes. I concur. Great. Okay. Thank you, everyone.
Thank you.
Bye.